Good evening, class. Welcome to week 2 of Living Systems 1, and we'll also be presenting lecture 2 for this week, Atoms and the Periodic Table. But before we do that, I just wanted to remind everyone that you do need to get yourself a lab coat for prac classes. So for students doing weekly prac classes, prac started today, and I know some of you still don't have your lab coats and had to hire one. So make sure you get onto that. Remember, you can go directly to La Trobe University, the Co-op Bookshop in Bundoora, and buy your lab coat for approximately $28. Or you might choose to order online through Live, Work and Playwear, and that'll cost you $36, but they do deliver directly to me at Epping, at the Epping campus. So I'll have that ready for you within a few days. All right, so make sure you all get onto that. Obviously, for the students that have signed up to the 2-day prac intensive workshop, which occurs later in semester, you don't need to hurry too much to get that lab coat organised. All right, so I would like to start with a slide that we went through last week. And just give me a minute while I come to it. Here we go. So you remember last week looking at this slide, and it's simply a way of classifying matter. So remember that matter can be classified as either pure substances or mixtures, and then this category here, pure substances, can be further subclassified into elements or compounds. Tonight's class, we're going to focus on this group here, the elements, with just a brief mention of compounds. So remember, elements cannot be broken down into simpler substances by a chemical change. All right, for tonight's class, we're also going to use what you can hopefully see on this slide. This is called the periodic table of the elements. And there is a copy of this exact periodic table on Moodle for you. So when you get a chance, I'd like you to print this out. If you're an online student, face-to-face students received a copy of this today. And there are many different versions of the periodic table of the elements. If you do a quick Google search, you'll find so many, and some of them are really pretty, really, you know, contain a lot of information. But I want you to focus on this exact copy here, this version here, because in the final exam, this is the one that you'll be provided with. Okay, so make sure that you stick to this version here during your studies of living systems. All right, so I'll come back to that periodic table of the elements. Now, let's begin our lecture tonight, lecture 2, Atoms and the Periodic Table. All right, so once again, what is an element? It's a pure substance, one group of pure substances, and these can't be broken down into simpler substances by a chemical reaction. Each element is identified by a 1 or 2 letter symbol, and we'll look at that in just a moment. All the elements known to man are arranged in that periodic table of the elements. And they're arranged in a very special way so that when you actually look at the location of a particular element within the periodic table, its location actually tells you so much about its chemical properties. And that's essentially what we're going to learn tonight. So let's look at the 1 or 2 letter symbols that accompany each of the elements. And you'll see this also on your periodic table. And I like that version of the periodic table because it gives you the complete element name and it gives you what's called the element symbol, obviously an abbreviation for the element name. So the symbol for bromine is simply Br, calcium Ca, carbon C, chlorine Cl, chromium Cr, and so on. So these are most of the common elements and their symbols. And you can see that the element symbols here are derived from the name of the element. So we've got cobalt, copper, fluorine, hydrogen, iodine, and then we come to these odd ones. So for lead, you would expect L. Instead, we have Pb. Any idea what that Pb actually stands for? If you've done chemistry before, you might remember this very odd name.
It's plumbum?
Plumbum, exactly right. Yes, which
Latin.
is the Latin. That's the Latin name for lead. So that's where the Pb comes from. Then we've got magnesium, Mg, manganese, molybdenum, nitrogen, oxygen, phosphorus, potassium. What about this one? Who remembers this? K. Why is potassium referred to as K? And obviously potassium is a very important one for agriculture, agronomy, viticulture and winemaking students. Any memory of this one? Any memory of what the K stands for?
Something to do with potash, and is it kalium? I can't remember.
Yes, kalium. That's exactly right. Kalium is the Latin for potassium. And another odd one here, this is an important one for students to remember because this comes up all the time. Sodium Na.
Is natrium?
Natrium.
Oh, natrium.
Natrium, yep, that's it. So natrium is the Latin name for sodium and hence the Na. And then we've got sulfur and zinc. So they're element names and element symbols. Now, let's look at this version of the periodic table. This is the one that's provided in the prescribed textbook. And you can see why I don't like to use it. You've got the element symbols here, but not the element names, which makes life difficult for students that have never studied chemistry before. Okay, but now we're going to look at some really important features of the periodic table. Important features that you need to remember. There are certain things that you just simply have to commit to memory for when it comes time for exams. All right, so let's start with a look at some of the elements and the numbers that they're associated with. So, H, hydrogen, it occupies position number 1 on the periodic table. Then to find number 2, we have to skip over to the right, and here it is, this helium, and it's given the number 2. Number 3, back over to the left, is lithium, Li, number 3. Number 4, Be, that's beryllium. And then over here, 5 for boron, 6 carbon, 7 nitrogen, 8 oxygen, 9 fluorine, 10 neon. So you can see how the numbering system works from left to right. But of course, sometimes you have to skip from one side of the table to the other to actually find the next number in that sequence. All right, so that's pretty straightforward. Let's look at the total number of elements, and there's not many. Here we have only 103, so this is not a complete periodic table of the elements. We're actually up to about 118 as of 2016, but all the new ones that have been added here, sorry, we're up to here, not 103. My mistake, we're up to here, but you can see some gaps there. Yep, we're up to 118 now. These gaps have been filled, but the new ones that have been entered into the periodic table of the elements have been synthesized in the lab. They're man-made elements. All right, so that's it. That's all the elements known to man. That's it. That's not many. As I said last week, considering that we know of millions of different compounds, but only 118 elements. That's amazing to consider the fact that all matter on Earth is composed of these basic elements. Quite amazing just to think of it in that way. All right, so how many of these are naturally occurring? Approximately 91 of these elements are naturally occurring. And the reason I say approximately is because there's many scientists that believe that anything up to 100 of these are actually naturally occurring, but there is still debate there. So that's why I say approximately 91 are naturally occurring. Okay, let's start with some features now. Okay, at the top here, you'll see a numbering system, actually two numbering systems. The top one here uses 1A, 2A, and then we jump across to find 3A, 4A, 5A, 6A, 7A, 8A. And then we go to these shorter columns in the middle here, 1B, 2B, 3B, and so on until we get to 8B. So that's one numbering system, and this is a numbering system for each column of elements in the periodic table. Then we have a different system, which is also widely used, and it goes 1, 2, 3, so the bottom numbers, 4, and then across here, 12, up here, 13, through to 18. Okay, so two different numbering systems. I want you to use the top numbering system, the 1A, 2A, 3A, and so on. Okay, so when you actually print out your copy of the periodic table, make sure you cross out the second numbering system. We won't be using that. Even though that's widely used also, there's certain benefits to using the numbering system that I like to use, and you'll see later on why that's the case. All right, so this is the numbering system for the elements found within each column. And instead of saying column 1A, we actually refer to it as group 1A. So group 1A is represented by all these elements in the first column. Group 2A elements are all these elements in this column. Over here, 3A elements are here, 4A elements here, and so on. Okay, and the same thing applies to these short columns in the middle with their respective group numbers. So we say group 1A elements, group 2A elements, and so on. Okay, so take note of that. That's very important to know. Next, the rows of elements on the periodic table, starting with the top row, and you can see the number 1 there. So the first row contains hydrogen and helium. So only 2 elements in the first row. But we don't say row 1, we say period 1. So note that, also important. Period 1. Period 2, the second row, contains lithium, beryllium, jump across, and period 2 also contains these elements here. Okay, row 3, and of course we say period 3, contains the elements across there, and so on. Okay, so that's groups and periods, and that brings me to this box down the bottom here. Okay, so these elements down here, which we never refer to, we tend to only use or refer to the elements in the top 4 or 5 periods. That is those of us within the life sciences, which is what you're studying. Okay, so back to these 2 rows down here. They actually belong in here. Can you see that little gap there? That's where they actually belong, in there. But for various reasons, they don't go in there. They're left separately, and there are no group numbers, as in group 1A, group 2A. No group numbers are assigned to these elements here. They do belong to period 6 and period 7, but they don't fit within those group number categories. They don't share the same properties as those other elements do within those groups. Okay, so as I said, we never refer to elements within these 2 periods here. All right, the next important feature on the periodic table. And here it is, this bold line here, which is also on your copy of the periodic table. There's a bold line indicated there. And on this copy here, you'll see some brown highlighted boxes. Well, it looks brown in my eyes. And these 7 elements that are highlighted here are referred to as the metalloids. They're called metalloids. Here's the term here, metalloid. So when you have your periodic table of the elements, you'll need to be able to identify which of those elements are the metalloids, just using that bold stepped line as your guide. All right, now let's look at all the elements to the left of the metalloids. All the elements to the left. Here they are. All the elements to the left are classified as metals. So this is very important to know the distinction here. They're all metals with one exception. Who can tell me what the exception to this rule is?
With regards to
there's all the elements to the left of the metalloids are metals except for one of them.
Hydrogen.
Hydrogen, good. So remember, that's the exception to the rule, to the metals rule, as I say. All right, now what about all these elements to the right of the metalloids? They're all called non-metals. There we go. All right, so an important one that you need to remember. Okay, I think I've covered everything there. All right, just very briefly, some of the features of metals, non-metals and metalloids. So metals, as I said, are located on the left side of the periodic table, with the exception of hydrogen, which is on the left side, but it's not a metal. They usually exist as shiny solids. They're good conductors of heat and electricity, and all the metals are solids at room temperature, except for mercury, which has the element symbol Hg, and this is a liquid at standard room temperature. Okay, what about the non-metals? They're located to the right of the metalloids, and this group also includes hydrogen. So make sure you note that over and over again, because over the years, students just forget that and they get it wrong. Non-metals don't normally have a shiny appearance. They're normally poor conductors of heat and electricity. And there are solids, liquids and gases within this non-metal group. So some examples, sulfur and carbon normally exist as solids, bromine as a liquid, and nitrogen and oxygen as gases. And finally, the metalloids. The metalloids are located on that solid line that starts at boron and then angles down towards astatine. And the metalloids tend to have intermediate properties between the metals and metalloids. So here are the 7 elements listed here. So make sure you can identify those on the periodic table. All right, now I said that we were concentrating on elements tonight, and we certainly are, but just a brief mention of compounds. So remember, compounds are the other type of pure substance. Yep. And a compound is a pure substance formed by chemically combining 2 or more of those elements on the periodic table together. And in fact, most of those elements don't exist in nature on their own. They exist bound to 1 or more other elements. And that's probably why there are so many compounds known. All right, let's look at what we mean by chemical formula. Chemical formula consists of the element symbol to show the identity of the elements that are forming that compound, and it consists of subscripts to show the ratio of the atoms in the compound. So this is one that everyone's familiar with, H2O, which is the chemical formula for what?
Water.
Water, yes. Everyone knows H2O. Even kids know H2O because of a very popular TV series called H2O. All right, so what does this tell us? We have an element symbol there, H, which you know stands for hydrogen, and we have another element symbol, O, which is for oxygen, and then we have here a subscript, the number 2. And when you see a subscript placed after the element symbol, that means that there are 2 hydrogens. In this case, there's no subscript, so we have 1 oxygen. So 2 hydrogens and 1 oxygen will make up 1 molecule of water. 1 molecule of water. If you were to divide or split those apart, you would no longer have a water molecule. So this is the basic building block, if you like, not building block, wrong term. The basic structure of water. The basic structure of water is this molecule of water. Here's another example here, C3H8. So that's simply telling us that in this particular molecule, there are 3 carbons and 8 hydrogens. And I normally refer to them at this stage as particles, but they're correctly referred to as atoms, and we'll come to atoms in just a moment. So this tells us, this chemical formula tells us that 1 molecule of this particular substance, which is, by the way, is propane, is made up of 3 carbons and 8 hydrogens. Okay, so they're 2 examples of chemical formulas. And I'm sure everyone's familiar with propane.
Yes.
Propane gas, yes. Probably have it in your barbecue gas cylinder. Yes, yes, absolutely. All right, so enough about compounds for now. Oh, apart from this slide. All right, so we've seen the chemical formula for water, but we can also draw this particular compound in different ways. Here we have what's called the ball and stick representation. 1 oxygen in red and 2 hydrogen atoms in white. And this is useful because it gives you that visual of how those atoms are connected to each other. Okay, this is the space filling representation, and you've already seen this representation in week 1. And of course, different elements are represented by different colours. And you can see here actually quite clearly that the atoms of each of these elements are different in size. So we'll come back to that later on. All right, now let's move on. Structure of the atom. So all matter is composed of a basic building block called the atom. This is the basic building block of all matter. Just like the basic building block of all living organisms is the cell. Same sort of concept, same principle. All right, atoms, each atom is composed of 3 subatomic particles. Well, most of them anyway, I should say. There are exceptions to every rule. I have to say this every week because there's always exceptions. All right, so let's look at the 3 subatomic particles that make up an atom. And the number of these subatomic particles will differ depending on which element we're referring to. Okay, so let's look at these. Proton, neutron, and electron. So the atom of each element will contain 1 or more protons, neutrons, and electrons. Proton carries a charge, carries what we call a +1 charge, a positive charge. A neutron is uncharged, so we say 0 charge or neutral. That's easy to remember. Neutron, neutral, proton, positive. An electron also carries a charge, but it carries a single negative charge, a -1 charge. All right, let's look at the mass in grams of each of these subatomic particles. Proton. Each proton has a mass of 1.6726 by 10 to the minus 24. Is that a very large number or a very small number?
Very small.
Very small. That's an incredibly small number. Incredibly small. Imagine trying to write out that many zeros to represent that number. This is where errors are made, and this is why we tend to use scientific notation to denote these exceedingly small numbers. All right, so that's the mass of a proton. A neutron is almost the same. 1.6749 by 10 to the minus 24. So they're almost identical. But because these numbers are so small, scientists actually came up with a standard mass for protons and neutrons. And the units that they use are AMU, which stands for atomic mass units. So this standard mass that applies to subatomic particles, for each proton, we say that it has a mass of 1 AMU. Same thing for the neutron, because it's almost identical in mass. So we say that a neutron has a mass of 1 AMU. Now let's look at the electrons. The mass of an electron, 9.1093 by 10 to the minus 28. Incredibly small. So small, in fact, that it's actually said to have no mass or negligible mass. So when we look at calculating the mass of a particular atom, you don't take any notice of the electrons. You just look at the mass of the protons and the neutrons. Okay? All clear so far?
Yep. Yes.
Yes. Excellent. All right, so let's look at how an atom is structured. So what we have here is one atom, one single atom. In the center of each atom, you'll find this tiny sphere called a nucleus. And within the nucleus, if we enlarge that, oh, here it is enlarged so we can see what's inside. This is where we find the neutrons and protons. So the neutrons indicated in red and the positively charged protons indicated in blue. So they're always found in the center of an atom. So location of the protons and neutrons is in the nucleus. This is the dense core of the atom, and it's the location of most of the atom's mass. Because remember, it's the neutrons and protons that have a mass of 1 atomic mass unit. Where are the electrons found? They're found in this cloud region here, moving around within this region, and that region is called the electron cloud. The electron cloud is the location of electrons, and it comprises most of the atom's volume. So that's the general structure of an atom. All right, so how do you work out, how do you calculate the number of protons, neutrons, and electrons in an atom of a given element? All right, let's start, and this is from the periodic table. Here's element number 3 on the periodic table. It's lithium. There's the element symbol Li, and you can see on the periodic table this number, number 3, and that tells us a lot about an atom of lithium. That number is called the atomic number. That's given the abbreviation Z. Atomic number tells us the number of protons in the nucleus of an atom of that element. In other words, if we looked at an atom of lithium, it would have 3 protons in its nucleus. Every atom of lithium, so every atom of a given element has the same atomic number. So that means that every atom of lithium on Earth, well, from what they've tested anyway, has the atomic number of 3. So they all have 3 protons in their nucleus. And think about this, the proton, the number of protons rather, determines the identity of the element. That's what determines the identity. So An atom, a given atom of a given element, can change its number of neutrons, it can change its number of electrons. It doesn't matter, it will still be the same element. But if it changes its number of protons, then it's no longer that element, it's something different. Okay, so that's what I mean when I say it's the protons that determine what the element is. Okay, so of course you can imagine that different elements have different atomic numbers, and you can see that from the periodic table. Now, what we're looking at today is only neutral atoms. That is, an atom that has no net overall charge. We won't be looking at charged atoms until next week. Okay, so a neutral atom has no net overall charge. So that means that the atomic number Z, which tells us the number of protons, must also equal the number of electrons. Let me explain that, and I'll just get my pen. All right, so let's imagine 3 protons, and you know that each one carries a positive charge, a single positive charge, so I'll indicate that there. And now let's put in some electrons, and each one carries a single negative charge. Okay, so if you've got 3 positive charges and 3 negative charges, which lithium has, by the way, then they balance each other out. They balance each other. So that overall, the overall net charge is actually 0. It's neutral. Okay, so that's all we're looking at today, these neutral atoms that have the same number of protons and the same number of electrons. So, I'll just get rid of my pen. Get rid of that. Okay, so key take-home message. The atomic number tells us the number of protons and, by default, the number of electrons in a neutral atom. Okay, now the way that we see the elements on the periodic table, it actually appears at first glance that there's only one type of each element. But in fact, most of the elements on the periodic table exist in different forms. So for example, there's different types of carbon, and there's different types of chlorine and so on. And these different types of the same element are called isotopes. Isotopes are atoms of the same element that have a different number of neutrons. So remember, their number of protons doesn't change, so they're still the same element, but the number of neutrons can change. Okay, so that brings me to a new concept here called the mass number, and the abbreviation is A. The mass number will tell us the number of protons plus the number of neutrons combined. Okay, it will tell us the total number of both protons and neutrons. All right, now if you were to look at your periodic table of the elements, oh, let's have a look because I've got it right here. Let's look at the periodic table of the elements. Okay. And now I want you to look at this one here, element number 17, chlorine, and have a look at this number down here, 35.45. Okay, let's keep that in mind, 35.45. And I'm going to write this down. 35.45. Okay, if we round that number, down to 35, then we have what's called the mass number of chlorine. Here it is right here. The mass number of chlorine, 35. Here's the atomic number. So remember, chlorine was element number 17. And this is an odd representation of chlorine. where we place the mass number as a superscript up here and the atomic number as a subscript, and they're placed before the element symbol. This can be a little bit confusing because those numbers are in reverse relative to how they're found on the periodic table. Did everyone notice that?
Yep.
Yep, so chlorine on the periodic table has the number 17 above it and the number 35 below it. So you've just got to remember that in this representation of chlorine, they're in reverse. Okay, so once you know that the atomic number of a particular element, in this instance chlorine, is 17, and you know the mass number, which is 35, because we rounded down that 35.45, then you can determine the number of protons, the number of electrons, and the number of neutrons for any given element. Let's look at that. Number of protons found in chlorine, found in an atom of chlorine. Well, we know that from the atomic number 17. There it is there. The number of electrons, how many electrons does the atom have? Well, the same as the number of protons in a neutral atom, 17 once again. Then all we need to determine is the number of neutrons in that atom. All you do is take the mass number and subtract the atomic number from that. 35, take away 17, so one atom of chlorine has 18 neutrons. Very simple. Yep, everyone follow that? Yep. Terrific. All right, let's move on. All right, so that number that we had up here, the correct expression for that particular number that's always found immediately underneath the element symbol on the periodic table is actually the atomic mass, the atomic weight mass. I've got it written here as atomic weight. We can use them interchangeably, but if you want it to be scientifically correct, then you would actually say the atomic mass. So that number, and the reason why this is not exactly 35, the reason why it's not a whole number is because it's an average. The atomic mass or atomic weight is actually the weighted average of the masses of the naturally occurring isotopes of a given element. And it's reported in AMU, atomic mass units. So, for example, another example here, this is carbon. It occupies position number 6 on the periodic table. So, of course, that 6 is the atomic number, Z. And then under the element symbol, it says 12.01. This is the atomic mass or atomic weight using the units AMU. Now, carbon has 3 naturally occurring isotopes. Carbon-12, this is the most abundant. 98.9% of all naturally occurring carbon is carbon-12. Carbon-13, 1.1%, so not particularly abundant. Carbon-14, even less abundant at 0.0001%. So these are the 3 isotopes, 3 different isotopes. These first 2, carbon-12 and carbon-13, they are very stable. This one is a radioactive isotope of carbon. So it does decay radioactively over time. All right, so that's isotopes. And now we're just going to look at how to determine the atomic mass or atomic weight of an element. You don't need to be able to do this, but just if you see how it's done, I think you appreciate it even more. So the example, what is the atomic weight of chlorine? Step 1, you need to be able to list each isotope. And here they are here, chlorine-35 and chlorine-37 are the 2 isotopes. You need to know the mass of each one. So an atom of chlorine-35 has this mass, 34.97. Chlorine-37 has this mass here. So you can see one smaller than 35, one larger than 35. Then you would need to know the isotopic abundance of each. Chlorine 35 is the more abundant. Chlorine 37 is less abundant. Those percentages are converted, as you can see here. And then you multiply the isotopic abundance by the mass of each of the isotopes and add them up. So here we go, 34.97 multiplied by its abundance equals 26.5. And here's the other isotope multiplied by its abundance. And those two are added together. And here's the answer, 35.45 AMU. And that's why this is what you see on the periodic table. Okay? So you can appreciate why the numbers are the way they are. All right, let's look at some more features now found on the periodic table. Some more important than others. Okay, firstly, we know that each row in the periodic table is referred to as a period, and each column of elements is called a group. Here's another grouping here, the main group elements. The main group elements consist of the two columns on the far left, I should say the two groups on the far left of the table, and the 6 groups on the far right of the periodic table. And these groups are numbered 1A through to 8A. So they're all the main group elements. Then we have the transition metal elements, and they're found in the 10 short columns in the middle of the table, and they're numbered 1B through to 8B. And then we have the inner transition elements that we rarely talk about. These are the consist of the lanthanides and actinides, and there are no group numbers assigned to these. Okay, so here we see period numbers indicated, group numbers indicated, lanthanides down here, actinides in the bottom row, and we've also got some colour coding so that you can see which ones are the main group elements in darker blue, transition metal elements in these short rows here, and the inner transition metal elements. Okay, not particularly important apart from the main group elements. They're the ones that we tend to deal with a lot. All right, let's look at some more groupings on the periodic table. All the elements found in group 1A, so remember that's the first column on the left-hand side. All the elements here are called alkali metals, with one exception. What's the exception to the metals rule?
Hydrogen.
Hydrogen, correct. Okay, so all the group 1A elements are alkali metals except for number 1, hydrogen. All the group 2A elements, so those in the second column, of course, are called alkaline earth elements. Properties of both groups: soft and shiny metals, low melting points, good conductors, and react with water to form basic solutions. Don't worry about that last statement for now. We talk more about that in a much later lecture. All right, now this is an important group. This is the one that I really want you to remember. Group 7A, the second last column on the periodic table. These come up all the time. These are called the halogens. So commit this one to memory. The halogens, let's look at some properties. The halogens exist naturally as 2 atoms joined together. The halogens come up all the time during any study of chemistry because they are so reactive. They combine with many other elements to form compounds. They're highly reactive, the halogens. All right, so let's look at the halogens because they're so important. Periodic table, here we go, group 7A. All the numbers are reversed here. I only just noticed that, or I've just forgotten. All right, the halogens are found here: fluorine, chlorine, bromine, iodine, astatine. No, not astatine, just these first four here. Okay, they're the halogens right there. All right, and finally, the very last group on the periodic table, group 8A, these are the noble gases. We very rarely talk about the noble gases because they tend to be so unreactive. They're very, very stable. They never combine with any other elements. Sorry, I should say rarely. They don't in nature, but they have been forced to react under very extreme conditions in the lab. So they're the noble gases. All right, now we're going to talk about electrons. Now, the electrons, as you know, are found within the electron cloud surrounding that central nucleus of the atom. But they don't just move around anywhere within that electron cloud. They're thought to be confined to specific regions within that cloud, and that gives each electron a specific or particular level of energy, depending on where they're found. Now, the regions occupied by electrons are called principal energy levels or shells, and that word shell is abbreviated to N. The shells are numbered, N equals 1, N equals 2, N equals 3, etc. And I'm going to show you roughly what this would look like. So let's say that's the nucleus. This would be the first shell closest to the nucleus, so that's N equals 1. And this would be N equals 2, N equals 3. Can everyone see that okay?
Yep.
Yeah. N equals 4 and so on. Okay, so that's how you can imagine it. N equals 1, N equals 2. Oh, that's dreadful. You'll get used to my dreadful drawing, by the way. All right, and so on. Okay, so that's what the shells look like, or principal energy levels. Now, the electrons that are found in the lowered numbered shells, so for example, N equals 1, they're closer to the nucleus, and those electrons tend to be held or bound tightly to the protons, to the positively charged protons within the nucleus. So because they're held more tightly, they tend to be lower in energy. The electrons further out, so in the higher numbered shells, they're further away from the nucleus, so you don't find that same sort of attraction between the positively charged protons and the negatively charged electrons. So those electrons tend to be higher in energy, which means that, as you'll see later on, those are the electrons that tend to be reactive. They're the reactive ones in a given atom. Okay. There we go. All right. So the shells with larger numbers are further from the nucleus, so they have a larger volume and can therefore hold more electrons. So N equals 1 can only hold a certain number of electrons. N equals 2 can hold a few more. N equals 3, more again, and so on. Let's look at the distribution of electrons in the first four shells. Shell number 1, the smallest one, can only hold 2 electrons. Shell 2, 8. Shell 3, 18. Shell 4, 32. So we can see as the number of electrons increases, as we're moving further away from the nucleus of the atom, then the energy level of those electrons also increases. All right, now here we start to get a little bit confusing. So we need to focus on this. Each shell is divided into one or more subshells. The subshells are identified by the letters S, P, D, and F. There are more subshells, but we don't go any further than this. Subshells S, P, D, F. Each subshell consists of one or more orbitals. And an orbital is simply a region of space where the probability of finding an electron is high. Each orbital, regardless of where it's found, regardless of the subshell that it's found in or the shell that it's found in, can hold only a maximum of 2 electrons. All right. I need my pen for this. All right, let's look at shell n equals 1. This one here has only an S subshell. And an S subshell, which you can see here, contains only 1 orbital. So how many electrons would you find in an S subshell? Given that each orbital can only contain 2 electrons.
So 2.
Only 2, yep. Okay, so regardless of where the subshell, the S subshell is, it can only hold 2 electrons. Oh, and by the way, here's the abbreviation for electrons. E is a little negative there, 2 electrons. All right, let's move on. Shell n equals 2 has an S and a P subshell. Okay, so we know that S subshell only has 1 orbital, so it can only hold 2 electrons. A P subshell, on the other hand, has 3 orbitals. So how many electrons could that hold?
6.
6, that's right. Yep, 3 orbitals, 2 electrons in each, so it can hold, a P subshell can hold 6 electrons. All right, next shell, back up here. Shell n equals 3 has an S, a P, and a D subshell. Here's a D subshell, and it has 5 orbitals, and that means it can carry a maximum of how many electrons?
10.
10 electrons. There we go. And finally, an F subshell. Oh, sorry, I should have written it up here. Go S, P, D, F. And I said to the students today, you've just got to remember that order, S, P, D, F, 1, 3, 5, 7. So come up with some way of remembering S, P, D, F. And someone did, and now I remember it myself. They said, Spudif. Spudif. I don't know why that really stuck with me, Spudif, for the SPDF. Anyway, subshell F contains 7 orbitals, so that holds a total of what?
14.
How many electrons? 14. 14 electrons. Good. All right, so once you know this, then given a particular, an atom of a particular element, you will know where to place the electrons, in which shells, in which subshells, and how many electrons each one can actually hold. All right, let's lose the pen. All right, so this table shows exactly what I've just explained to you. So here's shell number 1. The shell number 1 has an S subshell. So shell 1, S subshell, only 2 electrons can be found in an S subshell. Maximum number of electrons, 2. Shell number 2 also has an S subshell, and it has a P subshell. But the reason this is written 3 times is because there's 3 orbitals in the P subshell. And that's why it's written like this. It can be a bit confusing. But anyway, how many electrons can be found in a P subshell? 3 orbitals times 2 electrons in each for a total of 6. So in total, shell number 2 can hold 8 electrons. Okay, so that's how to read that table. All right, just very briefly on the shape the shape of these orbitals. And we'll just look at two of them. So the s orbital has a spherical shape, just the way that I drew it to the left of screen. But the p orbital actually has a dumbbell shape, as you can see here. So there's one p orbital, there's the second, and there's the third. And here they are all together, drawn on the same set of axes. Okay, I just draw them all spherical, otherwise you can imagine it would be a mess and impossible to follow. All right, now how to determine electron configuration for a given element. This is something that you need to be able to do. So we're going to run through a few examples. So the electron or electronic configuration describes how the electrons are arranged within those shells and subshells and orbitals. The lowest energy arrangement is called the ground state. And that's all we'll be doing. We'll be determining the ground state electronic configuration. So when we start placing electrons in shells and subshells and so on, we place them in the lowest energy shell and orbital, beginning with the 1s. Then we fill the remaining subshells in order of increasing energy. So that essentially means we start from here and we work our way out, even though it's not always that clear. And this shows you why it's not always that clear. So when you're given a particular element and asked to determine the ground state electronic configuration of that element, of an atom of that element, you would first look at the periodic table and determine how many electrons an atom of that element has. That's your first step. You need to know how many electrons it has. Then once you've determined that, then you know how many electrons you need to place to determine electronic configuration. So first you start with the shell number 1. It has an S subshell, so you would place 2 electrons in that. Then you start moving out. Shell number 2, or N equals 2, S subshell, place 2 electrons there. Then if you still have more electrons to place, move to the P subshell and place a maximum of 6. Maximum of 6 electrons go there. If you have more electrons to place, move to shell number 3, S subshell. Remember that can only take 2 electrons regardless of where it is. Then you move to the P subshell in shell number 3, and you need to know how many electrons to place there. Now here is where it gets a bit tricky. Let's say you had more electrons to place. Instead of going from 3p to 3d, you have to go from 3p to 4s, fill that subshell first, and then you would fill the 3d subshell. And the reason for that is because it's been experimentally determined by scientists that the 4s orbital is lower in energy than the 3d orbital. So you have to fill that first because that's the one that would be naturally filled first in the ground state of an atom. Okay, so you can see that there are a few of these funny fill orders, but you don't need to know any further than that level there. All right, so remember each orbital holds a maximum of 2 electrons. And don't worry too much about rule 3 because this applies to a certain way of doing electronic configurations, which is shown here, which we won't actually be using. So when you're determining electronic configuration, you can use this particular system where a box represents each orbital and a single electron is denoted as an arrow. An electron pair, so 2 electrons, are denoted by an up arrow and a down arrow. All right, this system here is called orbital notation. We're not going to use that system. We're going to use the electronic configuration system. All right, so let's look at exactly how this is done. Starting with this element, hydrogen. So determine the electronic configuration for hydrogen. If you're asked that question, you would immediately go to your periodic table. Well, you probably won't have to, because you'll probably remember that the atomic number of hydrogen is number 1. And the atomic number, remember, tells us how many protons are found in that particular atom. And by default, it tells us how many electrons. So we know that we need to place 1 electron into what's called an electronic configuration. So here's the electronic configuration for hydrogen, 1s1. That's it, that's all it is. What does it mean? The number 1 tells us the shell number, so n equals 1. The S tells us the subshell, so it's an S subshell. And how many electrons are found in the S subshell? Only 1, because that's all that's found in hydrogen, 1 electron. Okay, let's move on to another example. You're asked to write the electronic configuration of helium. You go to the periodic table, find out the atomic number Z, and you see that it's 2. That tells us 2 protons and therefore 2 electrons in a neutral atom. So you know you only have to place 2 electrons. And this is how you write it. Shell number 1, S subshell, and you pop the 2 electrons here. Done. Very easy. Another example, lithium. Periodic table, atomic number equals 3. So we know lithium has 3 protons and 3 electrons in its neutral state. We start writing out the electron configuration. Shell 1, S subshell, we put 2 electrons in there, that's all it can hold, but we need to place 1 more electron, so we move on to shell number 2, S subshell, and put the 3rd electron there. Total of 3 electrons, we have the electron configuration for lithium. Carbon, write the electronic configuration, go to the periodic table, atomic number equals 6, 6 electrons. Here we go. We always start with shell 1, S subshell, only holds 2 electrons. Then we have to move to shell 2, S subshell, put 2 electrons there. Now we have to move on to the 2p subshell and pop another 2 electrons there. Total 2, 4, 6, and we have completed the electronic configuration for carbon. Neon, Z equals 10, so it has 10 protons and 10 electrons. And here we go, 1s2, 2s2, 2p6. Done. Total of 10 electrons there. Okay, and finally, one of the funny ones where the order doesn't quite go in the right order. Calcium has 20 electrons according to the periodic table, and I just need to clear something here. There we go, that's better. All right, electron configuration. We need to place 20 electrons for calcium. 1s2, 2s2, 2p6. Now we move on to the third subshell, the third shell rather, n equals 3. 3s2, 3p6, 4s2. Okay, can everyone see what's happened there?
Yeah, we've gone back to the S.
Yes, exactly right. Instead of going 3S, 3P, 3D, we've skipped the D and we've gone straight to 4S. Okay, so remember that little trick for one of your tutorial questions. And if you don't remember how that order goes, refer back to the previous slide. I think it was slide 28. To make sure you're filling the shells and subshells in the right order. Okay, another feature on the periodic table, which relates to what we were just talking about. The periodic table is divided into blocks. The S block, which you can find here, groups 1A and 2A. Then we have the D block, these ones in the middle, and the P block and the F block. And all this tells us if an element falls into a particular block on the periodic table, that means that it contains, that indicates the outermost subshell that contains electrons. So let me just explain a bit further. So all these elements here, atoms of all these elements here, contain their outermost electrons in an S subshell. All the elements that are D block elements contain their outermost electrons, in a D subshell, and so on. Okay, we don't usually use these different blocks, but there is one tutorial question. So keep it in mind just for that. All right, moving on to a new concept, and this is a very, very important one. So if you're getting tired, don't worry, so am I. But we need to, I really need to focus on this, and so does everyone. All right, the concept of valence electrons. All right, so we said earlier that the protons within an atom determine the identity. But it's the electrons that determine the chemistry of a given atom, because it's the electrons, or at least some of the electrons, that are the ones that participate in many chemical reactions. They determine the reactivity, how stable a particular element is. The chemical properties of an element depend on the most loosely held electrons. Which ones do you think are the most loosely held electrons? And we mentioned this a little bit earlier.
The ones in the furthest away shell.
Exactly right. The ones that are furthest away, they're the ones that tend to be most reactive. They're found in the, those electrons are found in what's called the valence shell. This is the outermost shell of a given atom, outermost shell, which contains electrons. So the valence shell is the outermost shell, the highest value of N, which contains electrons, and those electrons that are found in the valence shell are called valence electrons. Let's look at this. Let's look at some examples. So here we have beryllium. Here's the electronic configuration for beryllium, 1s2, 2s2. So shell n equals 2 is the outermost shell that contains electrons. So we say shell number 2 is the valence shell. How many valence electrons does beryllium have? It has 2 valence electrons. Okay, so don't confuse valence electrons with total number of electrons. Let's look at another example, chlorine. Here's the electronic configuration for chlorine. What is the valence shell of chlorine?
3.
3, yes. So the outermost shell that contains electrons for chlorine is shell number 3. How many valence electrons does chlorine have?
7.
7, correct. Yep, so shell n equals 3 has 5 and 2 electrons, so a total of 7 valence electrons in the valence shell. Okay, good. All right, elements in the same group number on the periodic table tend to have very similar electron configurations. And as a result of that, elements in the same group on the periodic table have the same number of valence electrons. So this is where knowing where a particular element is located can tell you even more about its properties. So for example, we can use the group number 1A through to 8A to tell us how many valence electrons a particular element has, where the group number equals the number of valence electrons only for the main group elements. We can apply this rule. And there is an exception to this rule. The exception here is helium, which is found in group 8A, but it doesn't have 8 valence electrons like the others in that group. It only has 2 valence electrons. And the chemical properties of the elements in a particular group are similar because they have the same electronic configuration of valence electrons. So let's look at that here. So just for the main group elements, we can apply this rule. So remember from an earlier slide, main group elements are found in groups 1A, 2A, through to 8A. So we can look at the elements in group 1A. Okay, and there's only 3 shown here. And we can tell immediately, just because they're in group 1A, that all these elements have 1 valence electron. If we looked at all the elements in group 2A, there's only a couple shown here, then we would know immediately, because they're in 2A, they have 2 valence electrons, and so on and so on. So this is where this particular numbering system, 1A, 2A, 3A, in contrast to the 1, 2, 3, 4, comes into its own. Group 7A, remember the halogens, the really reactive ones? These have 7 valence electrons. Only 2 of them are shown here. Group 8A, the elements in this group have 8 valence electrons with 1 exception. Here it is. Helium is the exception to that rule. It has only 2 valence electrons, not 8. Okay, something else that you need to be able to do is to draw an electron dot symbol. Very simple. If you know how to work out the number of valence electrons for a given element, then it's very simple to draw an electron dot symbol. So dots representing valence electrons are placed on the 4 sides of an element symbol. Each dot represents 1 valence electron. And let's look at some examples. There we go. So here's the example, hydrogen, which has 1 valence electron, and here's the electron dot symbol. 1 dot represents that 1 valence electron. Next example, carbon. Carbon is found in group 4A on the periodic table, so that tells us immediately that it has 4 valence electrons. Isn't that much easier than actually writing out the electronic configuration when you need to determine number of valence electrons? All right, to draw the electron dot symbol, we write the element symbol as shown there, and we place 1 dot there, 1 on each side. And I'll just go around, 1 per side, and there we have it. Oxygen is found in group 6A, so it has 6 valence electrons. To draw the electron dot symbol, you can start wherever you like. I normally start at the top. 1, 2, 3, 4, and now we start to pair up the dots. And there is a reason for this, which we'll talk about in another lecture. And there we have a total of 6 valence electrons. And finally, chlorine. Chlorine's one of our halogens. It's found in group 7A, so it has 7 valence electrons. And here we have the electron dot symbol for chlorine with its 7 valence electrons. Okay, so that's fairly straightforward, assuming that you remember how to determine the number of valence electrons for a given element. And I'm not sure why. I say this every year, but every year it happens. Students tend to confuse this one here. For some reason, instead of drawing 6 valence electrons, they draw 8. So there's some confusion that goes on there with oxygen. All right, nearly there. 2 final slides for this lecture. And this is another trend that we see on the periodic table. Sorry? Oh, you've got a question. Yes, thank you. All right, the question here is, does it matter where the dots are placed, in which order? No, it does not matter. So if there's only 1 valence electron and you place it on the left or you place it on the right, it doesn't matter. Yep, good question, thank you. All right, but it will help you later if once you've actually placed an electron on each side of the element symbol, then you start pairing them up as you go around. Okay, that will help with something later on. But as I said, doesn't really matter. It's the number that's important. All right, thank you for the question. All right, our second last feature of the periodic table. And this is how to look at the increasing or decreasing size of the atoms of each of the elements, how to determine which one's larger than the other. So atomic size, the size of the atoms increases down a column as we move down a particular column. So if we were to look at a particular column, as we move down, the atoms of these elements will get larger and larger. And that's because the valence electrons tend to be further away from the nucleus. Atomic size decreases as we go across a row. And that's because the number of the protons in the nucleus increases. So if you've got more positively charged protons in the nucleus, then they exert a greater pull on the electrons, pulls them closer to the nucleus, and it makes the atoms smaller. Okay, so that's a feature of the periodic table. We never really use this, but there is one question, one tutorial question that relates to this slide. So don't forget that one. And finally, ionisation energy. Ionisation energy for a given atom is the energy needed to remove one of its electrons. And we'll talk about this in a lot more detail next week. So if it takes a lot of energy to remove one of the electrons, then that particular atom has a very high ionisation energy. If it's very easy to strip one of the electrons off, it has a low ionisation energy. Ionisation energies will decrease down a column. So if you were to just go down a particular column, the ionisation energies of these atoms gets lower and lower. Ionisation energies also increase as we go across a particular row. And that's because the number of protons in the nucleus increases. And that completes our lecture for tonight. Well done, everyone. How did you go?
Yeah, good. Oh, is that okay?
All good?
Yep.
All clear on everything?
Yes, I've just got 2 questions.
Yes, yes, please.
First of all, how do we know what's a neutral atom, or does it not matter? You said that we were only...
Yes. Good question, good question. If the atom was not, or that particular element that's written on your tutorial questions, if it was not neutral, then a charge would be indicated.
Okay.
It would say +1 or -1 or +2 or -2. If there's no indication of a charge, then you're looking at a neutral atom.
So I guess, Silvana,
Yes.
that last sheet that you've got, like the sodium there just above the arrow, that's a good example of a...
Oh, exactly right. Yeah, absolutely. So here we go. So we know that this sodium, Na, is charged because of that positive symbol there. Yeah, absolutely. Yeah, so Liz, you might be referring to one of the questions which actually confused quite a few students. And it was a question, maybe it was a question that asked you to state the charge of each atom. So if you haven't looked at one of the questions on your this week's set of tutorial questions asks you to actually state the charge of the given atoms. And of course, there's no positive charge indicated, there's no negative charge indicated, so they must have a zero charge, a neutral charge. Oh, so they're neutral overall. Yeah, good question. Thank you, Liz. And any other questions?
No, I'm good.
You're good?
Yep.
Yes. Yep. Fantastic. What about you, Darren? How are you going? Oh, terrific. Need to revise the first half. Oh, yes. Sorry, I think I confused. Yeah, I confused Darren and Anthony with that question, but that's okay. Yes, yeah, you'll have to revise the first half, otherwise the second half can be quite confusing, definitely. All right, so what do we have in terms of tutorial questions this week? Here we have them. So these are on Moodle. Tutorial number 2, based on tonight's lecture, atoms in the periodic table. Are they assessed? Yes, they are. They are assessed, due by next Monday at 6 p.m. So remember, the quiz will close at that time. Assessment weighting 4%. Okay, so make sure that you get these in. Easy 4% for you.
Mm-hmm.
Relatively easy. Okay, I won't run through these questions, but oh, here we go. Here's the question that I was actually talking about before. It says, state the charge of each atom. And if we look at these two here, calcium and sodium, there's no indication there of any charge. Mm-hmm. Okay, so obviously zero charge or neutral for those two. All right. This one here, number 1, which group of the periodic table is known as the alkali metals? List them. Remember when you're answering this that there is one exception to the metals rule. Okay, remember that when you're answering that question. And one more thing, which I forgot to mention. So remember I said that the abbreviation for an electron, for a single electron, is E with the negative symbol. For the neutron, we normally use an abbreviation N, lowercase n, and for a proton, we just use a lowercase p. That's supposed to be a P. All right, so just some abbreviations that you will come across. All right, and that concludes our class.
Okay. Yep.
Well done.
All right. Yep. Yeah.
Thanks very much, Silvana.
You're welcome. Thank you, everyone.
Okay. All right.
And have a great week, and I will catch you all next week.
Okay. Thank you.
Thank you. Good night.
Bye. Bye.
Bye. Bye.